supporting 6 water tank on top. So let me just take you through its architectural plan. It may look like a simple design, but it's not because of some constraints and it's rigid design from the architect. It cannot be modified because we don't have a lot of ample space to work with. As you can see from my drawing, they have indicated we have an existing building just adjacent to this wall that we are doing here. So having said that, you can see the 6 water tank that will be seated on top here. And these 6 water tank will be transmitting a lot of weight onto our structure. So the means of transmitting this water tank or the weight of this water tank uh, down into the ground is what is making this design become more of technical. So having just shown you that, I can also show you I can also show you these as the general arrangement drawing that I've drawn, and you can also remember that some of the columns will be terminating as we move into the second floor, as you can see here, because remember that we have an existing building here, and this building has some eaves, extra the eaves of the roof. So we have to leave some space so that we don't end up removing the eave of the building. So once we come to our first floor, we will shift our beam a little bit. So we'll be having like a cantilever such design. So you can see how this is quite going to be a bit challenging design to work with. So if we come back to ProtaStructure, you can see that our failure mode is likely to happen at this point, just from our first analysis. However, this is what we want to look at, that we work around and fix it in this design. So before we get started, let us just get to understand the amount of load that will be contributed by the 6 water tank here. So we are just doing like a design analysis of our model so that you understand what you are going to work on. So in CAD in BIM, actually, we just don't just model or design, just do it practically. Like this, actually, I like a project that I'm working on that it's going to be implemented on the ground from a client. So in fact, we have to be not just practicing, but we are doing something that is very practical. So having said that, let's just go and see how we can calculate this loading that will be coming on here. Before actually we get into that load, I can simply just right click it and we just check it. If we just come here and we come to edit loads, let me come to edit loads, and then if you come to this is the dead load, you'll have it as 4.8, and then if you come, because you're using a okay, that's the dead. Yes, you can just give. So we have 3 types of loads. We have dead load, which is here, which is 4.8 kilonewton. And then we have the self weight of this building, which is here. And then we have again the live load here, which you can change its magnitude as 27. So we have it here. So just to show you how we can calculate these loadings that are coming on top of our building, we can simply come to there is something that I've prepared here, as you can see. So these are the 6 water tanks. So you have to get the diameter of the water tank and the height, and then from that you can be able to calculate the volume of this water tank. And with me here is actually specification of these tanks from the manufacturer. This is the manufacturer that brings the standard water tank. So we are going to use a 10,000 liter tank, as you can see here. So we are going to use this as our 10,000 water tank. And you can see with this tank, we have a longer tank and a shorter one, to mean that the height, there are some tanks which appear to be short. Let me just demonstrate here. There are some tanks which will simply appear to be a bit shorter, meaning that this height is short, but the base is quite wide. So that is the base will be a bit wider. So those are called shorter. And also they manufacture those which are longer, which the diameter becomes smaller, but the height becomes a bit longer. So they are called, these are the longer tanks. So obviously, you know that pressure will increase with height. So if we adopt these longer tanks, then we're going to get a different pressure here as compared when you adopt the shorter tank. I'm just bringing the engineering aspect in this design so that when working, we actually get it right from the engineering perspective. And then having said that, when we come to the our drawing, let's just see if the space on the architecture or the space will allow us to put these tanks here on top. So if we go to our AutoCAD and we try to just check the dimension, we realize that we have a restrained dimension that it will only allow us to adopt the longer tanks because the space here is not sufficient. Yes, you can see here. So this is the diameter of our tank. Let me just do it so that you can see. So this is the diameter of our tank, as you can see here. So this is the length of the width of our roof, and obviously this one will be the length. For that, we don't have a sufficient height of 5 point something to accommodate the wider tank. So we are going to adopt the narrow tanks. So the narrow, if you have a space of 4.6, that's the very basic 4.6 from our as our width, then we have tanks that can occupy a maximum area of 4.3, so that will be sufficient. So we are adopting these measurements. So by adopting these measurements here, let me just clean up. So by adopting this measurement, we have to calculate the amount of pressure exerted on our on the slab roof. So to do that, I've already done the calculation here. Let me just take you through so that you just see. So if you have a tank of 10-liter capacity, which will translate to 10 cubic meter, and if the density of water is 1000 and the gravity is 9.8, then you can easily get the total weight. If we get this weight as 9.1 kilonewton, then with the weight here, we can now calculate again the area of our tank. Remember, these are the dimensions that of our tank. This tank A. Tank A is the longer tank, or I can say is the tank which has a longer height here, but a smaller base, which will be accommodated with our slab. So you can calculate the area here by using pi d squared, the area of a circle, and you get it as 3.77. Having gotten your area, your load, then you can simply now calculate the pressure exerted. And this is now how you calculate the pressure will be given by P over pressure will be given by force that is coming in form of kilonewton over area. So if you do that, then you can actually now get this pressure here, which now we're going to get it as our load that we're going to transfer to ProtaStructure for design. So if you get it as 26.04, we will adopt 27 kilonewton just to be on the safer side. Kilonewton, meter, kilonewton, meter square. So this is the load that we're going to adopt. So you can imagine the amount of weight that's coming on top of this structure. It's quite a lot, and we have to see ways in which we're going to design. And remember that some of the columns also are terminating here. So it's really a challenging design. It's not simple as it looks. So having that in mind, there is also just to mention something. This I also did for tank B just to get what could have been the difference if we had adopted tank B with a wider base, and I just noted that its pressure will come to around 18. You can see that difference, almost 10 kilonewton difference. So, and this is what will be the difference, that's around 8 kilonewton. So with that being said, you can now proceed to ProtaStructure and just check that when you come to our loading here, just right click and then you come to properties. You can see the live load that we inserted under loads. Let me just bring it here. So under loads we have this live load as being like 27 kilonewtons. So you can see this 27 is here, is what I've actually used. And you can see if you use that with the current members that I'm using, there will be a failure on this. So however, now I'm going to just see what I can do, either to add the member sizing or to add some more reinforcement just to fix the failure, these beams that are failing on this side. So having said that, then I'll just request that if you don't have this architectural model, I'll leave the link in below so that you can download it and you can continue, or you can proceed to just try and practice and see if you can get the members correctly. You can always share with me, I can review it. This one I'm doing it for free actually. But if you really need a comprehensive class on structural design using ProtaStructure and other structural software like ETABS, Tekla, Series, and maybe also detailing in AutoCAD, or you need to consult or have a project that you feel that need to be reviewed or need to be redesigned, or just a fresh project you need to be worked on, you can see how thorough we go to specification to specifics to ensure that we bring a very optimized design. You can even see the column that I've chosen here. They're not of the same size. You can see these are a 200 by 200 column. This is a 650 by 250 column. Like I've just tried to really optimize this design so that it fits uh, both it meets the cost constraints and also it meets the design preference and desires and constraints on site. Thank you for listening. Please, if it's your first to be in my YouTube channel, remember to subscribe, like, and comment, and let me know what you wish me to bring forth next. Thank you so much.